One of my main findings has been, for instance, in computer vision, one of its source of power is that it learns its own representations. When we first started building machine learning systems, we wouldn't try to write down the knowledge of experts, but we would still talk to experts about, well, what are the features that you look at? What are the things you're looking for? And then we would try to code up feature detectors that would detect those and feed that into our learning algorithms. Okay, so my name is Tom Dietterich, and I have been working in the area of machine learning since about 1977. So actually, the field of machine learning kind of got its start in the late 1950s by a guy named Arthur Samuel, who was at the time working for IBM and built the first program that played the game of checkers at a sort of not a world-class level, but a pretty good kind of hobbyist type level player. But in the 1960s and 70s, the focus of artificial intelligence was not really on learning at all. It was mostly about trying to capture human knowledge, write it down in some programming language, or we use these things called rule-based systems. And in the early 1980s, there was a previous AI boom around things called expert systems, which were these you would interview an expert in a domain, say, maybe you wanted to identify mushrooms or to tell the poisonous ones, or you wanted to diagnose blood diseases or something like this. And then try to encode their knowledge in these, what now we would call them domain-specific languages, DSLs, specifically to try to capture that knowledge. And then there was a reasoning engine that could run and handle, diagnose new cases. Yeah. So I was in this kind of small, tiny subcommunity of people that thought that we could teach computers to do this by giving them training examples rather than by talking to human experts. And the very first machine learning workshop was held in 1980 at Carnegie Mellon University. I was a master's student, or I guess I just started my PhD, and we had about 30 people there. So we can fast forward to today. So over the years in my career, I've worked on a wide variety of both fundamental and application problems. My favorite mode of operating would be to find an interesting application problem and then identify a novel machine learning problem that needed to be solved. Yep. So in the 91-92 period, I worked in a startup pharmaceutical company where we were trying to use machine learning to optimize drugs, so drug design. We were about 30 years too soon. The company was not a success. But that's where I stumbled upon a problem that's now known as the multiple instance problem, which is, in the traditional machine learning setting, I give you an example, say a picture of a bird, and I say this bird belongs to this species. Mm-hmm. And I'm trying to teach the computer to recognize, I don't know, bluebirds or whatever. But with drug design, the idea was to say, well, here's the molecular structure of a molecule, and it is either actively binding to the binding site target for the drug, or it is not. But the trouble is that molecules actually wiggle around a lot, right? They are not rigid structures. And so we would not know which of the different shapes that the molecule could adopt was the one that's actually binding. If you think of it as a key, in a molecule isn't a single key, it's sort of like a collection of keys on a keychain. And we know in the lab, one of those is opening the lock. We just don't know which one. And so that was an example of what we would now call weakly labeled training data because it's not a perfect training example that says here's the picture and here's the category. So that was one of the things. And so over my career, then I've worked on problems in ecology and sustainability. Oregon State University, where I'm located, is a real giant in the area of ecology and oceanography and all these atmospheric sciences, these kinds of things. So I've collaborated with a variety of people in those fields, and in collaboration with Professor Carla Gomez at Cornell, she and I led a series of large grants from the National Science Foundation to launch a field that we called computational sustainability, but it was really doing computer science research to try to promote environmental and economic sustainability, social sustainability. Probably the most important direction that's coming out of that was something I was not involved in, but which is the application of computer science and artificial intelligence to the design of novel materials. And now we are seeing big applications in material science. And despite all the excitement about large language models and computer vision, if I were betting what's going to be the thing that will really have a transformative impact on the economy, it's going to be the development of novel materials and novel drugs, because those are going to greatly improve our capabilities, for instance, in industrial processes, in medicine, and perhaps also in things like carbon capture. So I think but I'm getting off from the topic of my story. So my story then continues to, for the last roughly 15 years, I've been worrying about what we might call the Rumsfeld problem of the unknown unknowns. Mm-hmm. So when we build an AI system, or really any computer system, machine learning, in fact, is fundamentally a kind of backwards-looking technology, right? We collect training data from the past, and then we teach the computer to be able to do well on that training data, and then we hope that the future is like the past, and so that I don't know, if we think about the diseases that a medical system is seeing, that there are no new diseases, that we see the same diseases as we've always seen. Or in the self-driving car, we see the same kinds of other vehicles, of bicycles, of whatever that we've seen in the past. And the trouble is, of course, that the world isn't stationary. It's not static like that. And so this, I feel like, is one of the fundamental vulnerabilities or weaknesses of our AI systems, is that they because they are sort of fundamentally conservative, backward-looking technologies, they need to become much more able to deal with novelty. Yeah. That they're looking at a patient that's got a new disease. I mean, if we imagine that the chest X-rays, and the first time a person with COVID-19 had a chest X-ray, the computer should have said, "This is different from anything I've seen before." So I've been working on that. It's sometimes known as the novel category problem, or the open set problem. There's a lot of technical names for it. But basically, how do we deal with novelty? And so I've worked on that in the setting of sort of cybersecurity and insider threats in organizations. I've looked at it in the context of computer vision, sort of generically, and also in industrial processes. So, for instance, detecting that something has gone wrong in a welding machine. That when it's made a weld, we want to detect that there's something wrong with that weld. It doesn't look normal, and flag that. So the award that I was given was kind of a lifetime career award for a long body of work in machine learning and artificial intelligence.
Yeah, and most of, after expert systems, but for example, the novel material work, or some of this the robust AI work, are you still primarily looking at supervised learning systems, or are you now looking at them through the lens of transformer-based models?
Well, so I've mostly worked on the supervised problem, but one of my main findings has been, for instance, in computer vision, one of the problems with deep learning is that one of its source of power is that it learns its own representations. So it sounds like you're familiar with the problem of feature engineering. That when we first started building machine learning systems, we wouldn't try to write down the knowledge of experts, but we would still talk to experts about, well, what are the features that you look at? Do you look at the color? Do you look at for red, yellow spots on the corn plant, or what are the things you're looking for? And then we would try to code up feature detectors that would detect those and feed that into our learning algorithms. Well, with and we really had trouble getting computer vision to work terribly well with that, right? And so when the ImageNet challenge came along, the performance was not very good. And then when ideas from deep learning were sort of re-injected into the field in the 2011, 2012 time period, they just did vastly better on these computer vision problems. Right. And it was because they were able to learn their own representations. With the layers of deep learning, the deeper layers could learn to effectively to detect interesting image patches and patterns that should be present in order for it to be a giraffe versus a German Shepherd or whatever. And but what we've discovered is that when it comes to novelty and detecting something new, those representations don't work very well. The deep learning methods learn to represent the things that they're kind of lazy. They only learn to represent the things they're forced to represent. And so if you haven't given them any training examples for, say, an elephant, then when they're first shown a picture of an elephant, the trunk and the tusks maybe are not really even represented by the deep network. It maybe represents the feet, eyes, toenails or whatever, legs, but it doesn't say, oh my goodness, there's this huge thing growing out of the face of the elephant, because it hasn't seen anything like that in the past, so it hasn't learned representations for that. One antidote for that, though, is not only to train the system on the objects of interest, so not just the diseases in the X-rays or the bicycles and so on in the self-driving car, but to take a foundation model approach and try to train these systems to recognize everything we can think of, all the different kinds of objects in the world, and perhaps to do that with a self-supervised strategy. And the idea there is to try to capture as much of the variability of the world as possible, so that when we do see something, when it encounters something new, it can say, okay, well, maybe I've never seen an elephant before, but I have seen snakes. And so that thing looks kind of like a snake, except that it's got legs. So that combination of being a snake with legs, that's very low probability. It must be something new. And that's the kind of thing that I think that is the path forward.
Yeah.
It doesn't give us guarantees, but at least the system has learned to see everything that we know how to see, and I think that's the path forward.
Yeah. I've spoken a lot to Jan LeCun on self-supervised learning models and world models, and it looks like to me like the pre-trained transformer models really accomplish that. There's very little, if any, labeling of data. They just ingest the data and build their own representations of the world that then you can query. So in your latest work, how much has generative AI or transformer models, what kind of a role do they play?
Well, I would say in computer vision for object recognition, we've mostly been using the vision transformer models, but I'm not sure that they're significantly better than the convolutional neural networks. Images are not sequences of tokens, and we kind of have to artificially break them into regions in order to tokenize them. And the CNNs also incorporate some knowledge about the world, that it is two-dimensional and that it is translation invariant. So you move the camera around, it doesn't change the giraffe into an elephant. It's still a giraffe. And so I don't think the transformer models have had that much impact in computer vision for object recognition from a single frame. But once you put time into the picture and you're looking at video or something like that, then the transformer model, has this tremendous ability to flexibly look back into the past and find interesting relationships over time, and capture that idea that, in some sense, that if I change the frame rate in a video from 10 frames per second to 40 frames per second, that also doesn't change the world. But the transformer can deal with that instead of saying, well, I just look 2 frames back. Well, that won't work if I triple the number of frames per second. It needs now look 6 frames back or whatever. The attention mechanism can do that. And so I think transformers are extremely powerful as an exciting tool for us. But they tend to take more data to train, and they're more expensive to train. And so what the right combination is for any particular application is kind of an open question. But
and you talked about multi-instance learning. Can you talk about that a little bit? Because, and I don't know if it's at all related, but increasingly with transformer models, the trend is toward not a single model, but stacking models or having models debate each other. So I was curious what multi-instance learning was in that context.
Yeah. So it's I think where multi-instance learning comes up, for instance, in computer vision, as I said, it's a kind of weak supervision. So, if you were training, so I've worked on, for instance, data from camera traps in Africa, right? So you put out a camera with a motion detector, and when an animal walks by and sets out the motion detector, then you take a few shots, still frames. And now we want to, count up, find all the animals in those images, decide what their species are, and count them up. But when we so the ideal, if we were making this into a supervised learning problem, the ideal would be to have a person, outline each animal, each of the gazelles or whatever in the image, and say that's a Thompson's gazelle, this is a Thompson's gazelle, this is a whatever. That would be very precise labeling, but it's very tedious. And so what we normally do is just say, show them the image and say, how many gazelles are in the picture? And they count them up and they say 8. Okay, so now we know there are 8 gazelles in this picture, but we don't know where they are in the image. And that's another example of this multiple instance problem. It's just a form of weaker labeling, and so now the vision system has to generate a bunch of hypotheses for what might be the gazelles. And if they say, and then there's 2 elephants and there's also a zebra, okay, you have to compare a bunch of different pictures and figure out, the zebras are these stripy things, and and so on. And so statistically, the systems can learn that they need more data. We make it up on volume, so more data, but each individual image provides less information.
Yeah.
Now, what you were describing is more of, let's say, an ensemble approach, where we combine multiple models, and in order to improve our accuracy on data. And of course, right now so the traditional ensemble approach had a big flowering back around the year 2000. And my most cited paper actually is just a kind of tutorial paper on why ensembles help and why they're so wonderful. They're kind of the cheapest way to win a Kaggle competition or something like this. But the kind of ensembling that we're seeing in deep learning is a little different, because the premise of ensemble learning was train 100 or 1,000 really cheap models and have them all vote. But an LLM is not a cheap model. Even a small language model is not a cheap model. And you have to pay the inference price of evaluating, running your input through all those models before you combine them. So people are taking a much more selective approach, like in the mixture of experts approach, where given the input, it tries to learn which experts might be relevant to evaluate. Right. And you can also think of these very deep, like the large language models, these very deep transformer networks, as essentially a whole family of models. The one that's only 4 layers deep, 5, 6, 7, 8, 9. And so you can do what's called early exit, right? Where you stick the input in, and if the model is already very confident of the answer after evaluating only, say, 4 layers or 8 layers, you can cut off the computation there and quit. Or you can do the computation all the way to layer 100, but you now have like 100 different votes, one from each layer, and you can combine those in some way to get a better assessment of your accuracy. So and then now we have things like O1. We don't really know what it's doing, but we have these systems that are built out of multiple calls to LLMs and even calls to different LLMs to do things like generating candidates, scoring candidates, ranking, and trying to assess uncertainty. And now we're seeing programming frameworks coming up to support that. So it's a wild and crazy time right now. I don't know that we have much theory to guide us there, but we're gaining a lot of engineering experience. And
That's
certainly with the onset of deep learning, experimentation and engineering have far outstripped the theory. So those of us on the academic side are really struggling to keep up and try to explain what's going on from a more mathematical standpoint.
Yeah. And to that point, before people really jumped on these transformer models, I was hearing complaints among researchers at the big conferences that supervised learning had been kind of studied to death, and that there were these incremental advances, but nothing was really changing. And then the scaling of the transformer models kind of changed the field, and then everyone ran to that. And that's where everyone is working. Not everyone, but the bulk of the field is working now. Do you think there's more? And then I speak periodically to Rich Sutton, another winner of the award.
One of my research buddies, yeah. Mm-hmm.
Yeah, and reinforcement learning has not fallen by the wayside, but it's used as a component in some of these models or systems. But do you think that there are areas of machine learning where there's yet to be really major advances, and that in the longer term, generative AI will be an important development, but there will be all of these other developments? I mean, a lot of people working on neurosymbolic systems, and again, I'm a journalist, but 5 years ago, the symbolic people were really out of favor. So, yeah, where do you think all of this fits in, or have we really moved beyond supervised learning and self-supervised systems? Hi. When you're building an AI assistant, one of the biggest challenges is making sure it actually understands and responds quickly, right? That's where Speechmatics comes in. They've got real-time speech to text that gives you over 90% accuracy and less than a second of delay, crucial for making interactions feel seamless. And with recent updates, they're now making 25% fewer mistakes than Microsoft, which means you're getting some of the best accuracy out there for things like customer service bots or voice-driven assistants. Plus, it works in over 50 languages, delivering results in just 700 milliseconds. If you're working on an AI project, it's definitely worth a look. Personally, I've been amazed by Speechmatics voices like Humphrey, which sound completely natural. If you're working on an AI project, it's definitely worth a look. Check it out at www.speechmatics.com/realtime. That's www.speechmatics.com/realtime.
Well, that's a lot of questions. Let me see. Uh, so in the area of supervised learning, of course, actually, even before transformers, deep learning, right, really shook up the theory of machine learning, because we had all been studying the case where the sort of number of degrees of freedom in the models was less than the number of data points, right? So they were deliberately, we were very concerned about overfitting the training data.
Yeah.
And so we would use regularization and other kinds of restrictions to prevent the model from overfitting the training data. And really, Ensembles was part of that story as well. But there were already signs of a conceptual. I'm trying to think what the right crisis, I guess, in the sort of structure of scientific revolution sense, because there were some algorithms like boosting that where even after they had fit the training data, their accuracy on independent test data continued to improve as they were run longer. And there wasn't really a good explanation for this. And then with the deep learning, we saw that even more, that you could be training and your error would drop on your training data until it was essentially zero. And yet, if you kept training, performance on the test data continued to improve. And this was like super baffling, because our theory did not really explain this. And I think I don't think we still have a complete story there. There's been a lot of theoretical work on trying to understand what's going on, and we do have a much deeper understanding. But in fact, I mean, one of the most intriguing papers recently is by Jugate, I can't remember her first name, who's a professor at Toronto, showing that for these transformer models, that in order to achieve their sort of optimum performance, they must memorize a certain fraction of the training data, which would be a kind of overfitting. And of course, this is also very relevant to these questions about copyright and so on. So there's a lot of, so as I say, the theory is still trying to catch up with the practice. Now, that's still mostly in the supervised setting that's being analyzed. So let's see. Obviously, I would say the biggest lesson for artificial intelligence writ large of the LLMs is that if you can do your training as self-supervised, then you can scale to internet scale. And I don't think we'll forget that lesson. So there are many, many problems, I think, with LLMs and with statistical learning more generally. But anybody who proposes something new has got to show how it also will scale to internet scale. And that brings us to this question of neurosymbolic architectures of various kinds. I have a talk I've been giving on what I think is wrong with large language models. And one of the things I think is the biggest problem is that all this factual knowledge about the world is stored in the weights of these deep networks. And whereas I think that factual type knowledge should be stored symbolically, say in a knowledge graph or a database or some kind of explicit knowledge representation, because then it would be so easy to edit it and change it. Whereas these deep networks are really just giant monoliths that are very hard to update.
Right.
I mean, there are people obviously working on that, but I would say the current work on continual learning and deep learning has still really failed to give us any efficient way of doing additional training, aside from the kind of LoRa style things, which are still quite expensive.
Yeah.
So I guess I guess so that would be an example of a neural symbolic type architecture. Another one I'm really excited about is symbolic regression. So I've recently been seeing a lot of talks by physicists and atmospheric scientists where they are using these symbolic regression algorithms. There's a Python package called PySR, I think, that does some fairly straightforward work to try to find an algebraic equation, or maybe it can have transcendental functions in it too, but to fit data. And they are finding that this is much more interpretable, and that they can often, after they fit that symbolic formula to the data, that they can interpret physically what processes are being captured by different parts of the fitted equations. And so, at ICHCAI this year, there were some very nice work from Purdue on really improving these symbolic regression models. So that's a completely different line of research, but I think it's having a big practical impact in science.
Yeah, on that symbolic interpretation. What was the second word?
Well, it's called symbolic regression. So, in traditional regression, you have your input and then you have a real valued response variable.
Right.
Well, but we fit some sort of a deep net to that. But these folks instead are fitting an equation, so y equals f of x, where f of x is actually some, you give it some vocabulary of things it's allowed to use, logs and exponentials and sines and, multiplication, division, subtraction, and so on. And it searches that space of formulas.
Right.
Early work in this area was done back in the 1980s by Pat Langley working with Herbert Simon, one of Simon's very last research projects. But then it sort of didn't go anywhere. But now it's been taken up by scientists, and they are finding that even, I would say, kind of mediocre tools are actually extremely useful to them. And this has stimulated more machine learning researchers to come back and look at that problem again and see and so we're finding ways to scale up those algorithms to be quite efficient and effective even for fairly high dimensional problems.
Yeah, in that symbolic regression, you're building an equation to fit the data, and then can you take that equation and have it look at other data that it hasn't seen and extract from that data?
Well, you would use it to make predictions on new data.
Right.
So it's standard supervised learning, except that the model that's being fit is not, kernels or deep learning or decision trees or whatever, but it's algebra. It's algebra, right? So it gains immediately by interpretability if you give it meaningful input features. Now, if your inputs are lower level things coming from cameras or sensors or something, now you have this problem that the physical quantities of interest, say masses and accelerations or whatever, you're not directly observing and they're not directly given. So they would be latent variables. And this is going to take us back to Jan, say, in his JIPA models or something. Now we need to discover those latent variables in order to then express the function in some clean algebraic form over the latent variables. And I don't know of anybody who's working in that area. I'm sure some people are, but Jan certainly isn't. I mean, most of our trying to learn dynamical models of these systems, we're still using neural network models because we want the end-to-end differentiability. Whereas the symbolic regression is a discrete search, right, over a discrete space of algebraic expressions, so tree-structured objects, and it has all the problems of combinatorial search.
Yeah. You said that you're working on the application side. You were saying that the theory has yet to catch up with the practice, but you are working on the practical side, on the implementation side. Can you talk about that? What sorts of systems you're using? I know you did some work on wildfire detection, I think.
Right. So which will take us back to reinforcement learning, since I didn't answer your question there. Right. So I had a project wildfire management, and we formulated that primarily as a reinforcement learning problem. So the question we were asking there was, where should fuel treatments be applied? So right, a problem in the U.S. and other countries too is that throughout most of the 20th century we were extinguishing fires as quickly as possible, whereas the sort of natural fire processes of the ecosystem would have had fairly frequent low-intensity fires. At least in the Pacific Northwest, we would have had a lot of fires that would have come through and burned out the understory of the forest while leaving the big trees intact. And the Native Americans actually managed the landscape deliberately to try to achieve that. But because we extinguished fires very quickly, we had this big buildup of fuels in the understory of forests. And the result is that when we did have an ignition, it exploded with a very intense fires. So the question was, well, could we send people in to remove that accumulated fuel in the understory? And that's very expensive. So where's the best places to do that in order to try to control the sizes of the fires that might arise, say, from lightning strikes? And so that was a problem that we studied. Another one we studied was liability policies. So let's say you are one landowner and you own some patches of forest, and I'm another landowner and I own other patches of forest. If a fire starts in my land, say because I have not been doing a good job of fuel reduction, and it burns into your forest where you have been doing a good job of fuel reduction, shouldn't I be liable for your losses in your timber plans? And so we studied different possible liability regulations, and we were able to use multi-agent reinforcement learning to do that. So each landowner was choosing whether to apply fuel treatments or not to their land, and whether to harvest their trees for timber. So this is a very Pacific Northwest kind of model, and although it would work in the Southeast forests too. And the question was, should we have this kind of liability? Or should we just say, everybody has to pay for their own? Fire is a sort of act of God, and no one should be held liable. And what we found was that actually a policy that says, as long as you have been maintaining your fuel risk level at a reasonable level, then you should not be held liable for anything that starts on your property. And that other things that were more onerous kinds of regulations actually led to worse outcomes, because basically fire is very rare, despite all we see in the news, and so the chances that your land will actually burn are extremely low. And so there's a tremendous incentive to just hitchhike and rely on your neighbors and what they're doing to reduce their fuel loads to protect you. And as taxpayers, we sort of versus timber companies. Are the timber companies relying on the federal government to do the work, or actually it's actually more vice versa? The timber companies are doing a better job of managing their lands than the feds are, and so anyway, so that's the kinds of things we could study with reinforcement learning.
Yeah. It occurred to me, you were saying that your approach has always been to look at a problem and then figure out what flavor of AI could be applied to address that problem. Is that something that these new reasoning agents, I mean, you mentioned O1, could do? Match an AI system or to a particular problem?
So could they help us formulate problems? So right, if you think about a very standard thing you might a problem you might encounter in industry, say in, I don't know, chemistry or a lot of industrial processes, is that you'd like to optimize your processes, and so you might want to formulate, say, linear programs or quadratic programs and use big optimization packages to do this. And you might want to do that robustly, which is another layer of complexity. Formulating those problems correctly is very difficult. And maybe just as we can see that we can use LLMs to write SQL queries for us or to write code for us, maybe we could get them to also formulate these optimization problems. Mm-hmm. And that would be another example of a sort of neurosymbolic approach where you're using the broad world knowledge of the foundation model to help you do problem formulation, which you then hand off to a very specialized reasoning engine that is perfect for solving linear programs or something like this, or planning problems or scheduling problems, things like that. So yeah, I think there's a possibility there. I mean, I think these large language models are our first kind of thing that has very broad knowledge of the world. And we've never been able to build systems like that before. So for so much of my lifetime, our computer systems and our AI systems have been very narrow. And so we could, these systems could do very deep reasoning in their area, but they would often lack common sense. And I think one of so that they might draw a conclusion that just didn't make any sense in practice. And one thing I'm really excited about is actually closing the loop. So start with this large language model. Maybe it can say, formulate the reasoning problem abstractly, hand it off to a theorem prover or an optimizer, but then take the solution and come back and have the LLM evaluate it and say, well, I know this solution followed logically, deductively, mathematically from the problem I formulated, but it doesn't make sense. It's violating a bunch of common sense things. Let me reformulate the problem and try again, and keep doing that, because I feel like, the power of abstract reasoning is that you can turn the crank and it's perfectly sound reasoning. But the weakness of abstract reasoning is it throws away the context of the problem. And so when we get the answer, we always teach our students, now check your answer, go back to the original problem and say, does this really make sense or not? And this is where traditionally AI systems have failed, and where I think we have an opportunity now. So the other thing that I think that O1 and these other models are really showing is that if you look at the work that, for instance, Newell and Simon were doing back in the 50s, 60s, and 70s, they talk a lot about the problem of how do people, what they call evoke, the right knowledge to solve the problem they're currently confronting. So you put a person into a context, and somehow they're able to retrieve the knowledge that's relevant to that context out of the billions of things they might know. Well, at least large language models know billions of things. And what we're finding, and with our narrow AI systems, this was never a problem. They just didn't know enough. We could just retrieve everything because there just wasn't much there. But now with the LLMs, the trouble is there are these billions of things that they know. And this is why we have so much work on prompt engineering, because we're trying to evoke the right memories, the right pieces of knowledge from all of those scientific articles they've read and all of the newspapers. What's the piece of knowledge that's relevant to this situation? And so what I think is really fascinating is we're gaining a lot of experience with that right now, and people are even building tools to optimize the retrieval. So I think a lot about this chain of thought and so on. These are ways of trying to restate or transform the initial problem statement into a statement that will retrieve the right things when these systems go to their memories. So yep. I think it'll be I'm not sure that these are the best ways of representing all of that, but traditionally when we had too much knowledge retrieved, then you have another search problem that another combinatorial explosion that you retrieve too many things and you have to try them all out. And we're also hoping, I think, that when we do retrieve a bunch of stuff, that then the LLM can kind of score how relevant each of these retrieved chunks of knowledge is to the problem at hand and avoid that combinatorial explosion. So I think we're kind of groping and feeling our way in this area right now. But if we can solve that, then we can overcome the always in good old fashioned AI, we always would run into these combinatorial explosions. because the system didn't know enough to be selective on what reasoning paths it followed. So I think this is also extremely interesting. Yeah.
And do you think that these models, the transformer models, as they become more powerful or with reasoning, which it appears that O1 is an ensemble of models approach. I'm not entirely sure, but that
Yeah, we don't.
yeah, but that as the reasoning gets stronger, that these models could play a role in scientific research, in formulating hypotheses, and then working through problems.
Yes, I don't. I think I hesitate a little bit because I feel like LLMs are also vulnerable to all the problems of statistical learning. And so one of my favorite recent papers came out of Tom Griffith's lab at Princeton. The first author is Tom McCoy. Which is called Embers of Autoregression. It's sort of, I can't remember, it has a subtitle. But the basic idea is that they show that LLMs are very dependent on the training distribution, the distributions of the training data. So if there are problems that they have seen many examples of, they're much more accurate on those than on problems that they've seen have much less experience in, which is what we would expect from statistical learning. Similarly, they tend to, if the right answer to a question is actually a string of words that has low probability, they will instead kind of autocorrect that and output a higher probability string that is the wrong answer. And I think this is one of the sources of their hallucination tendencies. And so I think we have to solve this problem. And it goes right to the heart of statistical learning, which is that, supervised learning, unsupervised learning, all of these methods are extremely dependent on the distribution of their training data and very brittle to shifts in that training data. And I think that we need to try to find ways of training these systems so that they are much more robust to distribution shifts. Ideally, that we would have distribution independent learning, where you would learn facts and those facts would be true independent of the training distribution. So I'm still totally unclear about how that could be accomplished. But my intuition is that, at least in the parts of the input space where we have lots of training data, if we could also prove that our models are smooth in those regions, so they're not doing something crazy in between the training data points that they've had, I think we should be able to get a guarantee that they will perform well regardless of the probability distribution, as long as the distribution is sufficiently spread out. It doesn't concentrate. You can never protect yourself against, like, if all of your queries were on this one thing you always get wrong, you can't protect against that. But the idea would be that if there's some amount of entropy in the query distribution, then we would do things well. And I think that's also what we need for safety critical applications of machine learning. So I've been part of a National Academy of Sciences study on machine learning and safety critical applications that's been looking mostly at automated cars, automated aircraft, and medical applications, and looking at both traditional safety engineering and then what might need to change in order to bring machine learning into the picture. And I think the big problem is that there is no statistical learning algorithm that's going to give you 5 nines of reliability, right? Yeah. It's very rare that we even get something that's 99% correct in machine learning. It's usually in the high 90s, and we're very happy about that. So the solution to that conundrum is we need our systems to give extremely reliable uncertainty quantification, so that they can say, okay, I know how uncertain I am, and so I can guarantee that if I give an answer, it will be right with, say, 5 nines. And if I'm uncertain, then I will flag that and it will fall back on some other decision-making process.
Yeah.
And so that brings us to this problem of uncertainty quantification, which I feel is a huge issue for large language models. And there are maybe a dozen or so groups around the world trying to get good probability estimates out of these LLMs and trying to see how much that can remove the hallucination problem.
Yeah. Another thing people have talked about is curating the training data
Right.
in some way so that you don't have a lot of chaff or a lot of noise in the training data. Are there strategies that you've seen that show promise there?
Well, I guess traditionally the strategy was kind of an outlier detection, anomaly detection approach. So you would apply an unsupervised learning method to try to understand, map what the training distribution looks like, and then flag things. If you think there are errors in the input features, like measurement errors, for instance, then you could detect those. So you might say, well, someone who has a salary of $100 billion, that's very unlikely, or has, I don't know, an age that's a negative number. Things like this you could detect. Detecting bad labels in the supervised case is tricky because you basically have to impose some prior belief on how accurate the classifier should be. And then you can say, well, the points it's getting wrong, maybe they're mislabeled and we should ignore them, as opposed to maybe the points it's getting wrong are just the hard examples and you should learn from them. And that's a fundamental conflict that is ultimately not resolvable. It depends on really understanding where your labels are coming from and what their errors are. So if you can assess that and you have an idea what your error rate is on your labels, then you can say, well, then you can use that to guess which data points maybe need to be relabeled or downweighted or even deleted from the training data.
Yeah. I've spoken to people about using these large models as truth engines to be able to, if they're trained properly, to be able to present them with a question on which there's a debate, and the model would give you a probability score on one viewpoint or the other. Is that something that you thought at all about? Does that enter into your research?
Well, I haven't done research specifically on that, but I think we know that if we can have a reliable oracle, like if we think about the game of Go or chess, AlphaGo, it had a perfectly reliable oracle for whether it won the game or not. But that's an event that happens far in the future, and by using reinforcement learning and search, we can use that oracle to label our data, to label the games we won and the games we lost. Now, the trouble is LLMs are not very reliable oracles for a lot of things. But most of what I've seen of the attempts to use LLMs to criticize their own outputs have not been very successful. There's a technique for uncertainty quantification called p-true, which is where you ask the LLM to produce an answer, and then you ask it again, do you think this answer is correct or not? And have it just give you a yes/no score. And of course, it can give you a log probability along with that, and we use that as an assessment. That's a really terrible method. It doesn't score very well on the experiment. So I'm skeptical, but maybe there are ways that we could train good oracles for specific problems, and then the systems could right now say O1 is doing some kind of a search and it is scoring somehow its own results, and when it finds a result that it has very high confidence is correct, it could then train on that, right? And that would be a direction toward a form of self-improvement. So, but I think in general, if we look at the history of science and human beings, we generally have to go out and do an experiment in the real world to check a hypothesis. We can't use our own prior beliefs to say, well, it seems right to me, so I'm going to believe it. that leads you into conspiracy theories and confirmation bias. So I think I'm also very interested in the sort of automating science by hooking up LLMs and other machine learning technology to the so-called self-driving labs, where you can robotically design and execute experiments, get the results back, and then learn from that. So that's a really exciting direction.
Yeah, particularly in drug discovery. I've spoken to a number of people that have automated.
And materials and mathematics. And of course, O1 is particularly strong in mathematics. And that may be because, again, that's an area where you can check. Once you have an answer, you can check it, say, with a theorem prover or something.
Well, this has been fascinating. I really enjoyed the conversation. Is there anything you want to end with that I didn't touch on?
I guess just to the extent that there are students listening to this, I hope you get the idea that there are tons of open problems. AI has not solved whatever that would mean, and I think that it's a very exciting time and will be for a long time. I don't think that some sort of superintelligence is around the corner that's going to solve all these problems, but that we have many exciting things to work on, and I encourage people to join the field and join the fun.